especially for getting this accomplishment by our research project from 2008 to this year. Oh, sorry. Especially, I want to emphasize three topics in my presentations. One is the monitoring marine plastic debris, so microplastics. The second is the monitoring oceanic microplastics, especially microplastics drifted in the surface layer. The third topic that I want to introduce you is modeling, numerical modeling of oceanic microplastics for the current status and status in the near future, Okay, now I start my talk regarding the monitoring macroplastics. So that is the plastic debris especially on beaches. As you know, the investigating, surveying macroplastics, marine plastic debris on beaches has a long history in, for example, oceanography. But this procedure is very so-called very primitive. The top two panels, sorry, top two panel. Okay, these two panels show their photographs taken from the guideline for monitoring marine litter on beaches in the OSPA maritime area, published in European countries. Usually, we firstly determine the areas that we have to investigate. Thereafter, we measure the particle count, the number of the marine debris littered on the beaches by human power with naked eyes. So this procedure has been long been conducted in marine plastic research, but for example, now I'm showing you in the lower panel. In the lower panel is the result of the published by Rivik 20 years before. So his effort was very great. He measured the plastic debris on beach once in each month during 6 years. So this very intensive efforts make positive trend of the abundance of beach litter during 6 years. But however, we have to meet some difficulty to interpret this fluctuation with a very small, very short time scales within several months or several months. And we cannot find any seasonal variabilities. And these fluctuations seems to be very irregular. It's very difficult to interpret. Probably the prevailing time scale for beach litter varying time is much shorter than we might imagine, much shorter than we can monitor by field surveys, probably due to meteorological disturbances such as mid-latitude cyclones or something like that in the nature. So aliasing error might might mislead our understanding of the abundance of beach litters. We need the observation, the beach litter survey with much shorter time scale. So we have used the lab camera to monitoring the beach litter continuously during the long time. Now I'm showing you the photograph of a web camera installed on the west coast of the United States. So this project was conducted to monitor the marine debris generated by March 11, 2011 Tohoku Great earthquakes. the top grade earthquake. So you know that a huge amount of the marine debris was generated, this tragedy, and thereafter these marine debris washed ashore on the beaches of the United States and Canadian coast. So this may carry the invasive species to these beaches. So the monitoring of the marine debris was very important issue, very important project for the researcher in United States, Canada, and Japan. So in this research project, we installed a web camera at the top of the cliff along the facing the beach of Oregon coast. So this is a web camera facing the beach, and this camera is driven by the solar panel system, and this web camera sends all photograph images to the laboratories via internet, because this is a web camera. Now I'm showing you the movie created by the photographs taken continuously during 2 years, during 1 year, sorry. I forgot to say, this web camera takes the photograph every hour during the daytime, during 2 years. Okay. I'm showing you the movies created by the photographs. Oh, okay. We can find that the shoreline moves. This is not wave, but tide. Because our photograph taken every hour, every 1 hour. So during the winter time, the marine debris increase. The marine debris in this area is mainly composed of mainly result from the driftwood or lambas, not plastic debris, derivative beaches, but it's very easy to find the increase of the marine debris by the photograph. Sorry? Do you have some comment or questions? Okay, just a moment. Just a moment. Chat. Okay.
Participant, please mute your mobile.
We can't.
Somebody, mic is available. Can I continue my presentations?
Yes, sir.
Yes, sir.
Yes, sir. You can continue.
Okay. Just a moment. Okay, I continue. So in each photograph,
essential. After that, I will give you examples. Okay.
In each photograph, we can count the number of the marine debris like this, and we can make the time series. We can make a time series of the abundance of the marine debris within the photograph. Of course, the angle that we can take on the picture is not so large, but we can monitor the number of the abundance of the marine debris with a very, very, very short, resolution of the time scale. Resolution of the time scale is very small, very small. So we can make this kind of the time series. Now the red curve means abundance of the marine debris in the photographs. And this red curve, blue line means wind speed. So we can compare. Oh, sorry, some line appear on my PC. It's okay. And we can compare these two time series because our data set of the marine debris has a very short time scale. So this is one of our advantage for monitoring the marine debris by using the web camera. Now the web camera is also used in monitoring the marine debris around Japan Island. Okay. Okay, I will introduce another our research. All right. Okay. Now we have another new technologies to monitor the marine debris on the beaches by using the drone, so multicopters. We can take the photograph over a beach, within a very short time scale, and we can take the photograph in the in the different angles, And this I'm showing you are movies, which is integrated by the many photographs taken by drones. So the drone can take the photograph in different angles, so we can compute the volume of each marine debris as shown by the digit just at the side of the each marine debris. And the plastic debris has a very, very different colors, different from the ambient sand or rocky beaches. So using the difference of the color, we can identify the plastic debris, only plastic debris, by using the deep learning. So the combination of the drone monitoring and deep learning can make our system which can compute the total volume of the plastic debris littered on beaches. Okay, sorry. Okay, I again show our system. So each digit is the volume of each marine debris computed by the photograph taken by the drone, and we can integrate all volume. Thereafter, we can obtain the total amount of the marine debris, plastic debris littered on beaches. A plastic can be identified with deep learning by using the color difference between plastics and ambient sandy or rocky beaches. Okay, this has been already published in a Marine Pollution Bulletin this year. Now we are discussing with the Japanese government to use this system to monitor the marine debris on beaches around Japan Island. Okay, I have talked regarding the macroplastic litters on beaches, and next our topic is changed to the microplastic on beaches or in the oceans. As you know, the large plastic debris, macroplastic, has been degraded, and after degradation and fragmentation, it gradually changed to the microplastics. It's probably on beaches because the sunlight or oxidative breakdown reaction with water and oxidative breakdown has been intensively occur on beaches than in the seawater. And also the fragmentation by mechanical stimulation by waves and friction with sand occurs especially on beaches. So generation of the microplastic are believed to be intensively occur on beaches than in the sea, but it's very difficult to conclude that the generation of the microplastics is not be conclusive at the present time. And threat to marine biota or an ecosystem has been pointed out by laboratory-based studies. On the left-hand side, show this cartoon shows the microplastics absorb the persistent organic pollutants such as PCB on their surfaces, and by ingestion by organic marine biota, these polluted microplastic move to these marine biota, and thereafter Thereafter, the POPs and persistent organic pollutant move from the plastic surface to the body of marine biotas. This is one of the threats that we may encounter at the present time and in the futures. Another threat is shown on the right-hand side. The microplastic is not toxic materials. Plastic is not toxic materials, but if the marine biota takes a huge amount of the microplastics, this may change to the toxicity. So this is the particular toxicity may occur in the marine biota in the actual oceans. So many laboratory-based studies pointed out these threats of the microplastics. The important thing is to monitor the abundance of the microplastic in the actual ocean, to investigate whether or not the microplastic in the natural environment may threat to the marine biota in the nature. We have conducted the abundance of the surface microplastics, the microplastic in the surface layer around Japan Island, around Southern Ocean and the Pacific Ocean, and the part of the Indian Oceans to date. So, and microplastic survey around the East Asian Sea has started. 2014 is now continued sponsored by the Ministry of Environment Japan. And our research project conducted transoceanic surveys from Southern Ocean to Japan these years. The procedures are very in line with the conventional oceanography, especially for zooplankton studies. We use the mandatory or Newton net, surface net towing, like by showing this picture, this photograph. And this Newton net, this is a Newton net, and this Newton net is fixed at the sea surface by two buoys attached at the midpoint of the frame. This net has the 75 and 75 centimeters square, and in line with the conventional studies of the oceanography, this net has a mesh size of 330 micrometers. An important thing is that we have to attach the flow meter at the mouth of each net. This flow meter is required. This is a minimum requirement. This is a minimum requirement for measuring the microplastic, because this flow meter can measure the seawater volume of seawater passing through the net. If we don't have a flow meter record, we cannot record the volume of the seawater passing through the net, and it's very difficult to convert our microplastic count to the count per unit seawater volume. So attachment of the flow meter is a minimum requirement in surveying, in investigating of the microplastic in the surface area in the natural environment, in the actual oceans, Thereafter, we bring back all samples, all seawater samples with the microplastics and as natural sediment in the seawater, and extract the microplastics by hand, by human power. This is a very time-consuming processes. And very, very small microplastic, especially smaller than millimeter size, is very difficult to identify whether or not this is a plastic or not, this is very distinguished from non-plastic materials. So we use spectrometers such as FTIR like this, or Raman method, or something like that. Otherwise, it's very difficult to distinguish very, very tiny microplastic from natural materials, such as fragment of the biologically generated materials. And thereafter, for example, we take the photograph of each fragment to measure the size in size on a monitor using the stereo microscope. And in my laboratory, we use this kind of the size distributions. This axis, horizontal axis, show the sizes of each microplastic fragment, and vertical axis means the abundance with the unit of piece. Piece means a particle count, piece per cubic meter. Cubic meter means seawater volume, unit seawater volume. So particle count per unit seawater volume is shown in a vertical ordinate in the vertical panel, vertical axis. We can find that small microplastic number of the microplastic increase, we move to the small size. This is a matter of course, because small fragmentation makes the number increase and size decrease. So this kind of the curve is very natural. So all procedure has been open publicly on YouTube. You can see the movies on regarding the extraction of plastic from CO2 bottles, or extraction from plastic, extraction on filtration and analysis of FTL and measurement of sizes are all open to the public on YouTube. You can see the movies by getting these movies on your PC. But as I said, this is a very, very time-consuming and error-generated process in microplastic measurement. So we conducted inter-laboratory comparison experiment for measuring the abundance of the microplastic in the standard seawater samples. In this project, so researchers around the world attended. So we made two bottles with seawater and microplastic and natural materials, natural sediments. And all these standard samples distributed to these laboratories. So in these laboratories, counted the number of the microplastics. Oh yeah, participants ask for question in chat. Okay, if you have some question, you can type your question on in chat box in any time. I can interpret. I can stop my presentation to answer your comment or questions in any time. I guess it's advantage of this kind of the webinar. Please don't hesitate to ask your question to me in chat in any time. Okay. To create these standard samples, we made the man-made microplastics by using the metric mold like this. So we represent each microplastic, man-made microplastic by representing the microplastic, representing the microplastic actually collected from the oceans. So we made a man-made microplastic and small fragment and fiber shape, man-made fiber shape microplastics, and we made man-made microplastic with different color and different polymer type and different thicknesses and different sizes. And also we create man-made suspended particulate matters for this interlaboratory comparison experiment. So man-made suspended particulate matter are made from wood chips and shells and eggshells or cultured zooplankton free of plastics. We input all man-made microplastics and man-made suspended particulate matter within the two bottles with a seawater. So these two bottles were distributed to the participants of this research project over the world. So we know the solutions. We know the accurate number of the microplastic by each sizes before sending all participants. And of course, the participants did not know the accurate number. So all participants report the number of the microplastic that they can extract in their laboratories. Okay, laboratory A to L are the participants. So each laboratory has a different method. For example, filtration is some suction sealing or chemical treatment to remove the organic matter are also different. Some laboratories do not use this kind of treatment, but some laboratories use another method. And density separation to extract the light-weighted microplastic is also different by laboratories. Of course, sorry, this what a fraction from CO2 samples. I forgot this one. Size measurement is FTIR or so this using a microscopic, and polymer identification is FTIR or Raman, or some laboratories did not use the polymer identification by spectrometries. Okay, this is the results of our interlaboratory comparison experiment. Upper left-hand side for the sample 1 and right-hand side shows the sample 2. So as I said, I create two bottles. One bottle is for sample 1 and one bottle is for sample 2. And this red bus means the accurate, correct number of the microplastics that we input into each bottle by before distributing bottles to each laboratories. And this mark shows the number. This axis in the horizontal axis means the size of each microplastics. And ordinate shows the numbers. And as I said, the red bar means the correct numbers of the in each bottle, in each sample bottles. And this mark means these marks mean the number by size, different size, and counted by each laboratory, different laboratory. So overall, the number counted by each laboratory is in line with the correct numbers, but fluctuated by each laboratory, So the average and standard deviation for the numbers of the microplastic collected in each laboratories. So the numbers extracted the number of the microplastic extracted by each laboratory is not always identical. because of the difference of the procedures adopted in laboratories. Okay, results are summarized here. So this graph shows the relative uncertainty. N is the number of the microplastics extracted in each laboratory. N0 means the solution. N0 means the correct number of the microplastics in each sample bottles. And left-hand side shows, in this panel shows the effect of the efficiency of the FTIR spectrometry. And this axis means the size. And bars on the left-hand side is the laboratory with FTIR. The bar on the right-hand side means laboratory without FTIR. You can find that as far as the microplastic of the size larger than 2 millimeter, the difference of the laboratory with and without FTIR are very small, very minor. But regarding the microplastic with size less than 2 millimeter, the difference of the laboratory with and without FTIR are very large. In the laboratory without FTIR, the microplastics number of the microplastics are overestimated by 50% in comparison with the laboratory with FTIR. So it's very deep. So this experiment suggests the fact that if we don't use FTIR, it's very difficult to accurately quantify the number of the microplastic, especially for the size less than 2 millimeter. In other words, the microplastic larger than 2 millimeter is easy to distinguish by naked eye or using the stereo microscope to distinguish them from other materials such as natural marine biology fragments generated from marine biologies. Of course, and chemical treatment and density separation are very effective, especially for the microplastics more than 1 millimeter. Okay, this summarizes all our results. This upper panel shows our laboratories. Lower panel shows the best practice. Best practice means the laboratory using the FTR, using the chemical treatment or density separation. So even if we use the procedure with the best practice, the microplastics smaller than 1 millimeter is always underestimated by 20%. So this is our technical limit to quantify, to measure the abundance of the microplastic by these procedures, by the procedure that we widely use at the present time. Okay, we use some different units in my presentations for the microplastics. First, we use the unit with the particle count per unit CO2 volume, such as piece per cubic meters. This is the abundance. This is the abundance directly observed by towing net with a flow meter. However, this data, this abundance is very, very sensitive to oceanic conditions, such as wave or windy conditions, because there are wave and windy condition make oceanic turbulence make microplastic distribution is very vertically homogeneous. So microplastic abundance obtained by surface net towing is very sensitive to the ocean turbulence. So we have to remove the influence of the oceanic turbulence by using the formula like this. This bar chart means the vertical distribution of the microplastic abundance at the 0 meter to 1 meter and 2 meter and something like that. You can find that the microplastic abundance, the concentration of the microplastic decrease exponentially as we move to the deep layers. Because microplastic has mostly lightweighted, lighter than seawater, because mostly microplastic made from polystyrene or polyethylene or polypropylene, of which density is smaller than seawater. And if the ocean turbulence change to be very intensive, this sinusoidal curve change to be vertically homogeneous. So we we approximate this sinusoidal curve like this. AW means experimentally obtained experimentally obtained upward velocity of the microplastics. We usually use the 0.005 millimeter per second. And A0 means the vertical diffusivity. And vertical diffusivity is computed from the wind speed and wave height. So wind speed and wave height should be obtained as metadata when we collect microplastic in the natural environment. And thereafter we vertically integrate these equations. And there is the same as that one. So we can directly observe the microplastic abundance at the sea surface. And we vertically integrate to obtain this value. M is the vertical integrated particle count, total particle count in the entire water column. So this is independent of the oceanic turbulence because this is vertical integration. Vertical integrates varies. So this is used, for example, the piece per square kilometers. So we can recognize this is standardized concentration of the microplastic, from which influence of wave and wind, the ocean turbulence has been already removed. And sometimes we convert these particle count to weight by approximating shape of each microplastic fragment to cylindrical shape, thin cylindrical shape with the density of plastics. Okay, all procedures that I mentioned here has been opened publicly on the website of Ministry of Environment Japan as a guideline for harmonizing ocean surface microplastic monitoring methods, which has been published on the website of Ministry of Environment from 2019, and you can find this guideline by typing guideline and microplastic on Google or something like that. Okay, let's move to the topic on the microplastic. We have monitored the microplastic around Japan Island from 2014 to the present. These photographs show the microplastic that we have actually collected from the oceans of Japan Island. And we have collected microplastic abundance around Japan. On the left-hand side shows the panel on the left-hand side show the microplastic abundance with a unit of piece per cubic meters. Cubic meters. The largest cycle means 100. So we have observational point south of the Japan Island, but abundance is so very small in comparison with abundance around Japan Islands. So the abundance of the microplastics is much large in the ocean surrounding Japan. Left-hand side show the vertical integration to remove the influence of the wind and waves. To remove the oceanic turbulence caused by the wind and waves. So this bar means the so
Participants, please mute your mic.
okay. So the bar at the uppermost portion show the microplastic abundance with the unit of piece per cubic square kilometer by integrating vertically from the sea surface to the infinitely deep layers in the East Asian seas. And the second one is the average of the North Pacific. The third one is the average of the world oceans. These two values are published by the Erickson 2014. And the lowest one is the value in the Shetland Sea. Shetland Sea is located here. This is published by us 2014. So you can find that the abundance of the microplastic in the East Asian Sea is the largest over the world. So this abundance exceeds 1 million pieces per square kilometer, on a magnitude higher than that of the North Pacific and world ocean in the Sea of Japan. So she's my colleague from Indonesia, and we measured the abundance of the microplastic in the eastern part of the Indian Oceans. So surprisingly, the abundance of the microplastics, and this is counted by as a piece per cubic meter. So this is a raw RAW data obtained directly by net towing. So the abundance is higher than the abundance around East Asia. So the abundance of the microplastic in the Indian Ocean in the eastern part is very large. We are very surprising these large values. So this is the vertical integration to remove the influence of the oceanic turbulence caused by the wind waves and winds over the ocean. You can find that also the abundance of the microplastic in the Indian Ocean is higher. In general, the microplastic abundance in the Indian Ocean is higher in the ocean around East Asia, North Pacific here. So the number of the data obtained in the Indian Ocean is very small, only this area. So our concern is the abundance of these areas. I guess the abundance of the microplastic in these areas is expected to be very, very large, in comparison with the other ocean over the world. But this is just my guess, And this is the microplastic abundance from the along our survey tracking from Southern Ocean to Tasman Sea to the Equatorial Pacific and North Pacific. This panel shows the abundance with a unit of piece per cubic meter and the abundance of the piece per square kilometer. This is the vertical integrated value of the upper panels. And the left-hand side shows the Southern Ocean. This number 1, 2, 20, 38 is corresponding to these numbers. So number of the station numbers. So the Southern Ocean is located on the left-hand side of each panel, and the latitude moved to the north as we move to the left in each panel. So roughly say, the abundance of the microplastic in the Southern Ocean, in the South Pacific Ocean is about 10,000 piece per cubic kilometer, square kilometers. However, the abundance, magnitude of the abundance increased by one order as we move to the North Pacific. The abundance is 100,000 pieces per square kilometer. And if we move to the North Pacific, East Asian area, the abundance of the microplastic increase to the million piece per square kilometers. So the marine plastic pollution is a problem in the northern hemisphere, and especially in the East Asian area. The marine plastic pollution problem is very serious at the present time, and probably the situation is same as that in the Indian Ocean. Because the mismanaged plastic waste are very large in the countries surrounding Indian Ocean, as in the country in East Asia. Probably we may encounter the same problems. This is problems in the Asia areas. And as I said, we have found microplastic in the Southern Ocean. This is the first report in the world. And this is the first peer-reviewed paper on pelagic microplastic in the Southern Ocean. This is highly cited. This now become a highly cited paper in the top 1%, published 2017. So we have find the microplastic in the Southern Ocean. You know that plastic debris is generated in generated from everyday life, and the Southern Ocean is located the farthest ocean from everyday life. And the fact that we have find microplastic in Southern Ocean suggests that it's very difficult to find plastic-free ocean over the world at the present time. Now, microplastic survey has been conducted by many researchers during these 10 years. Now I'm preparing one paper. This is our latest accomplishment, our latest work. It's not published yet, unpublished. Now the manuscript is in preparation. So we integrate, we synthesize the microplastic surveys result over the world oceans. At the present time, about 8,000 surface net towing are conducted, and this is published in many different papers. We synthesize all data as shown in these panels. And the current dot means the location that the microplastic survey has conducted in the past. And the color means the microplastic concentration with a unit of piece per cubic meters. So as you can see, the microplastic abundance is very high in the East Asia area like this, and very high in the Mediterranean seas, and high in the so-called North Pacific garbage patch here, and probably here. So this area is located in the convergence zone of the ocean current in the mid-latitude. Probably the same area should be maybe appear in this area. So ocean convergence zone in the South Atlantic. So data in the ocean is very sparse, very small, but high value in the eastern part of the Indian Ocean suggests high concentration in these areas. It's very, we expect to increase the observations of the microplastic surveys in the Indian Oceans. Okay, this figure, this figure is created by integrating all result. This is the surface microplastic concentration by interpolating, by using the optimum interpolation method. in each month, So now you can find the changing months on the continent here. This is the, yeah, this is the now August, October, November, January, February, and color means the concentration with the unit of milligram per cubic meters, Okay, you can find that there are high concentration of the microplastic around Japan and the European countries, and even in Antarctic Ocean, Antarctic Oceans. And you can find here, the high concentration here. And using this result, we conducted numerical modeling to reproduce the microplastic abundance in the present time and to forecast microplastic abundance in the future. This has been published last year by Nature Communications. The title was Abundance of the Non-Conservative special meaning. I will explain later. Non-conservative microplastic in the upper ocean from 1957 to 2066. 1957 is 6 years before. This means that the plastic has been started to use in the world. And 2016 means the 50 years after. The model has a generation of the microplastic. The area of the model is Pacific, is restricted to Pacific at the present time. Now I'm extending our model to the world ocean, but it's not published yet. I'm showing you the published data, published result. So you can find some dots. This means the generation area of the microplastics. The generation of the microplastics are proportional to the mismanaged plastic waste estimated by Jambeck, 2015. And time series of the microplastic generation is proportional to the gross domestic product, GDP. So this is the emission model of the Jambeck and GDP model. And this numerical modeling use the ocean current and wind on the background. We use the high quality analysis ocean current in 2015, repeatedly used the ocean current in 2015 using these long-term computations. And we compute the Stokes drift over the world ocean by using the wave model. Wave model is driven by the satellite wind, and the current to transport the microplastic in the upper ocean is a combination of these two currents. So sum of the ocean current provided by the HICOM and ocean current computed as the Stokes drift carry the microplastics in the upper oceans. A Stokes drift is the ocean current generated by the wind wave. This is very important to to reproduce the microplastic transport in the model. So this is, in general, this is a particle tracking model from the generation of the microplastics by carrying by ocean current and Stokes drift. So this equation means the particle tracking model. But we add the sync term in this particle tracking model. So this means that the microplastic drifting in the upper ocean is not eternally drifting. So the oceanic process we assumed that the microplastic drifted in the upper ocean removed by oceanic processes, something like that. So sync term means the removal process of the microplastic by settling down by falling or absorbing into the sandy beaches or fragmentize into tiny, tiny microplastics that we cannot observe, we cannot model. All processes are including the think time. Think time is very simple in this model. We set the time scale year of the tau, and after the year of tau, the generated number of the microplastic reduced to e-folding, reduced by e-folding. So, and removal process is determined by randomly, but the total number of the total amount of the microplastic removed to reduced to e-folding at the year tau. So tau is not determined a priori. We have to determine the tau by try and error to adjust with observed result. Okay, this is the result of our numerical modeling that reproduces the microplastic abundance with the piece per cubic kilometer at the present time in February. This is the result without removal time scale, removal processes. So tau is infinitely large at the present time. So we can compute as shown by red dot. We can compute the zonal distribution of the microplastic around the same line, and dot means each mark means observed result. This means that so we can compare this slope by modeling and by observation, and by using the different tau for the removal processes. Results show that if we this is observed value, and this is the zonal slope, the slope of the concentration, in the zonal directions, and this observed value by showing each mark in this panel, and this other marks show the result of the numerical model with a different time scale for removal process. If we use the removal process with a very short time scale, so the slope is much higher than we observe. This area is probably appropriate from 1 to 3 years for the time scale to remove the microplastic from the upper layers in the model. Okay, another point, we can compare the time series of the abundance by using the historical value. And golden thing show the microplastic abundance in 2070s, 2080s, and 2019 and 2010. So this mark means the microplastic abundance at the eastern part of the North Pacific in this period. Another mark means the microplastic distribution or microplastic abundance in models with different tau. If we use very short time scale, large time scale, the abundance increase to larger than observed. Okay. In a viewpoint of the north southern slope, the short time scale is not appropriate. In the viewpoint of the long-term variation of the microplastic abundance, the long time scale is not appropriate. So we choose around 3 years for appropriate time scale to express the removal process of the microplastic from the upper layers. Okay, this is the result of the numerical model with the time scale of 3 years for removal process. The left-hand side shows the microplastic abundance at the present time. The right-hand side shows the microplastic abundance in the future, in the 50 years after, 50 years after, 50 years after. We can find that the very dense microplastic at the midpoint of the North Pacific here in the August, here at the present time, and in the 50 years after. Especially, the microplastic abundance exceeds 1,000 milligram per cubic meter in 50 years after in the East Asian area, in the midpoint of the North Pacific. We can compare this result with the laboratory-based studies to date, conducted to date, published to date. So this axis means, this graph means the result of the laboratory-based studies using the tank with aquatic biota inside. And each laboratory, these laboratory-based studies, so observer input the microplastics, and these marine organisms were exposed by microplastic in water tank. And each mark shows the result of each study with different species, fishes or bivalves or something like that. And we plot marks at which the aquatic or marine biota show the damages in this experiment with the microplastic with this concentration and this diameter of each microplastic, microbeads. The damage shows a variety of damage in each these laboratory-based studies. Some experiments show the increase of the mortality rate. Some experiments show the increase of the decrease of the size of each organisms, or something like that. So variety of damage appear in laboratory-based studies. Anyway, the concentration of 1,000 milligram per cubic meter. Laboratory-based study with the size 1,000 milligram per cubic meter is most frequent. So this means that if the marine biota, marine organisms exist in the water with a microplastic concentration larger than 1 milligram per cubic meter, so some damage will appear in marine biotas, and this concentration will be realized in the future here and here. So marine plastic pollution in 50 years after reach the levels at which marine biota, marine organisms show damages. However, I have a very serious weak point in this numerical modeling. That weak point is the difference of the size, the gap of sizes. We monitor the microplastic in the ocean by using surface towing net with a size of several hundred micrometers. So this means that the lower size limit of the microplastic that we monitor is several hundred thousand micrometers. And in the analyzing procedures, this lower size limit is also the technical limit. And our numerical model uses the observed result as for the validation. So numerical model and the microplastic in the numerical model has also a size limit with the several hundred micrometer. However, the laboratory-based study uses the plastic beads with much smaller 1 or 10 or nanometers for the experiment. So this large gap suggested that our model result cannot directly predict, directly forecast of the damage that may appear in the marine organism in the nature. So we have to bridge the size gap to forecast, to predict the future risk of the microplastic. This is the front line of the marine plastic research to date at the present time. Okay, this is a final PowerPoint. So we have to do this a to-do list towards the sustainable reduction of plastic in the world. So first, we have to uncover the generation and transport and fate of the microplastic in the world oceans. So we don't know how do microplastic generate. So use the emission model, but we have to investigate how the microplastic generate from the macroplastic, for example, the time scale or locations. So this is very important. And as I said, in a model, we use the removal process, and removal process is very roughly represented by the time scale of tau. Tau is expected to 3 years in an experiment. But however, we have not yet understand fate of microplastic after removing processes. So we have to uncover where microplastic go in the oceans. So now we refer the marine ocean marine plastic circulations. We have to elucidate the entire figure, entire state, we have to uncover the entire marine plastic circulations. Otherwise, we cannot forecast the future status of the marine plastic pollution accurately. And we need much accurate observations. As I said, the current observation is very time consuming. And we have a lower limit of the microplastic with size of several hundred micrometers. So we have to monitor the microplastics much smaller than 300 micrometers. And we have to standardize and harmonize the microplastic abundance to compare and to synthesize the microplastic data obtained by different research over the world. This is a very important task that we have to do at the present time. And of course, the risk assessment and the environmental friendly development of the environmentally friendly materials are very important in these problems. Okay, thank you very much for listening to my lecture. If you have questions, please type the question in our chat box. I try to answer to each.
Yeah, participants, if you have any doubt, please give your questions in the chat box.
Okay, I have one question. Okay, standard protocol for the seawater sampling and special product and sample. Thank you. So, okay, thank you very much. So if you have questions, please type on the chat box.
Participants, if you are having any questions, please type it in the chat box. Thank you.
No. Okay, we have one question. What is the standard procedures to collect seawater sample in and around estuary locations? Sample in and around estuary locations. Is there any specific protocol available and any distance in between sample point? This question is for the sampling in estuary. So we have a guideline for collecting the microplastic, but the guideline is for the oceans, not estuary, but probably the difference between the ocean and estuary is the existence of the very intensive current. But I guess procedure is not so different. So the guideline published to date is very useful for the microplastic observer for the estuaries. Please refer the guideline published that I introduced in this lecture or other guidelines. And so please ask me types of the FTIR, particularly for microplastic analysis. Types of the FTIR. So we use the ATR FTIR. If we have so many kinds of two kinds of the FTIR and micro FTIR. The difference is price. Micro FTIR is very, very expensive. FTIR is not so expensive. So first we use the FTIR, so just FTIR, and ATR type FTIR. We use ATR type FTIRs for identify the microplastics. And how we can implement the marine plastic in construction industry and what's the scope for that. We can implement the marine plastic in construction industry. Conduct industry, and what's the scope for that? So I don't have any good answer for this very difficult question and very important. And so probably first we have to monitor the microplastic or plastic debris around the construction industries in the actual situations. Thereafter, we can so say something to them. The important thing is to monitoring the current status. First, I guess so, and this is my answer, but I guess this is not so good answer, I'm very sorry. Yeah, we can share the standard protocols. So standard protocol, standard procedure has written in the guideline for example, this guideline. In this guideline, the procedure in collecting microplastic in the actual ocean and analyzing microplastic in the laboratory are all explained detail. So I guess that this guideline is very useful all for the researchers regarding the microplastics in the ocean and in estuaries. And any other effect on the coral reef in particular? My God, this is a very great question. Thank you very much. And I'm not a researcher for coral reef and a biologist, but I guess in my understanding, some research has already published on marine plastic on coral reef, because something they said in my understanding, small tiny microplastic cover the biological fall of the coral reef. This may prevent from coral reef to grow up. So you can investigate the influence of the coral reef. Investigating, you can find some papers on the influence of the microplastic on coral reef already published. And according to your study, we can see the alarming rise in microplastic by 2006. Yes, how we can reduce increase. It's very important. It's very important and very so critical questions. We have to. Sorry. In my understanding, this is my personal opinion. In my personal opinion, we have to reduce the total amount of the plastic products in everyday life, because the single-use plastic, some part of the single-use plastic is really moved to the oceans. So to stop the generation of the mismanaged plastic waste and so leakage of the plastic in the oceans, we have to reduce the total amount of the plastic products in everyday life. But the difficulty arises from the fact that the plastic is not the material of the rich peoples. Plastic are used in, especially probably in the poor people over the world oceans, over the world. So I have made some difficulty to rapidly decrease the plastic products in the world ocean. We have make a very good action plan to reduce the plastic product in line with scientific evidences. How and how increase ocean currents for spreading the microplastic how influence ocean current for spreading of microplastic in world ocean? Yeah, this is a very good question. And my major is physical oceanography. This is the question of my major. So ocean current make a convergence zone of the plastics. Microplastic and plastic debris are not distributed homogeneously over the world oceans. We have some convergence zone. This is made from ocean current, or made by ocean currents. So ocean current is very, very important to enhance the risk of the marine plastic pollution at the present time and in the futures. Okay. Feedback from link. Sorry. What's the feedback from link?
Yes, sir. That is for a participant to getting the certificate, sir. To fill this link, then they will be receiving the certificates, e-certificate.
Participant, any questions? You please put it in the chat box.
Yeah.
Any questions are there? Shall we conclude? Okay.
Okay. All questions finished?
Yeah, sir. Yes, sir.
Oh,
Sir, one
sorry.
more question is
Sorry.
yeah.
Just one question is appear here.
Yeah.
Before the characterization studied, how we can identify the
Yes,
presence of microplastic? Characterization studies. How we can identify the presence of microplastics. So this means that how we can identify the plastic without any spectrometric procedure. The answer is so if the microplastic has a size larger than several millimeters, it's easy. It's possible to identify the microplastic. It's possible to distinguish microplastic from other fragments by naked eyes. But if the microplastic has a smaller than several millimeters, we need spectrometric procedures. Can we manage to increase the biodiversity by reusing the marine plastics? Reuse. It's very difficult. In my personal opinion, it's very difficult to reuse the marine plastic to the plastic products. Because marine plastic has already largely degraded. So I think it's very difficult. At what depth of the microplastic sample collected? Yeah, we use surface net towing. So the depth is from the sea surface to 1 meter at the maximum
okay,
of the sea surface. Is there any strict law in Japan to reduce the usage of plastic? No. We don't have any strict laws at the present time. So general recommendation. We have only general recommendations. Sorry. Yeah. Okay. Yeah, so thank you very much for many questions. Probably I cannot answer some very question. I cannot good answer for some questions, but I enjoyed your discussion in chat.
Thank you, sir. Thank you, sir.
Yeah. Thank you very much.
Only one question, sir. At what depth the microplastic samples have collected, sir?
Oh, well, I already answered. So, doctor, so I get the we got the microplastic from the sea surface. Sea surface means from sea surface to the about 1 meter depth from the sea surface.
Okay, sir. Okay.
Okay.
Okay, sir. Okay, sir. So, participants, shall we conclude now? Okay, so I'm going to deliver our vote of thanks. Okay, it's my privilege to have been to propose a vote of thanks on this occasion. I, on behalf of Department of Civil Engineering and SRM Institute of Science and Technology (KTR) and entire supporting organizations here together on my own behalf of extend a very heartful vote of thanks to Honorable and valuable speaker ATCHIKO ISOBE sir for gracing your important work and sharing with us your findings. And your talk definitely encourage the young minds and inspire towards marine microplastics research. Once again, I thank you, sir. Heartful thanks to you, sir. And my sincere thanks to Dr. Sri Stella Madam, Head and Professor of Department of Oceanography and Coastal Area Studies to participating here. And my sincere thanks to Ramesh sir, Parthasarthi sir, Suresh sir, and Prakash from the DDP work, and all the participants. Once again, I thanks to all. This webinar, I definitely feel all got good knowledge about marine microplastics and this field as new innovation and a lot of research opportunities. Once again, I thank you all and my class students. This useful for your minor project. Okay, thank you all. Thanks, sir. Thank you very much. Sir. Yeah, sir. Thank you very much, sir. Sir,
Thank you very
valuable-
much.
Yes,
Thank you
sir.
very much.
Thank you very much, sir. Thank you very much.
Thank you very much. Goodbye.
Namaste, sir.
Namaste.
Namaste, sir. Namaste, sir.
Namaste.
Goodbye.
Goodbye, sir. Goodbye, sir.
Goodbye. Thank you very much. Thank you.
Thank you. Thank you. Namaste, sir. Yeah. Thank you. All participants, you fill your feedback, then you
Yes.
will be receiving your certificate. Okay, so if you want any standard procedure, we will share you very short. Okay.
Participants, please fill your feedback.
Can we leave, ma'am?
Yeah. You fill your feedback, then you leave.
Once you complete your
No,
feedback
feedback is
from
done,
different, no problem.
Thank you, sir.